Welcome to a video on atomic physics. Today I'm going to introduce to you three or more equations that are related to atomic physics, specifically this chapter in the book, which I did a bit of a 7-minute summary back in the day. I'm going to just show you guys a solution to a problem, like an example. We're going to go through the book and we're going to find a problem and we're going to tackle it point blank, as minimal cuts as possible. I'm going to try to do it just off the hip here. So the equations I want to show you guys are these ones. We got capital E subscript n is equal to Ke, Coulomb's constant, E squared, the charge of the electron. Then we have a 2, we have this A naught, and that's it over there. And then over here we have n final squared in the denominator subtracted by n initial squared. There's a similar equation here that looks very, very similar. Ke E squared to a 0, and then here we have a 1 over n squared. There's another equation that looks again very similar. Z squared over n squared. All of these are super, super similar. And actually you will find two other formulas that look very similar. It is this one for the wavelength, lambda. And another one for the frequency, which looks like this. Here we have a 2a subscript 0 and h, Planck's constant. And then we have n final squared minus n initial squared. These are the reciprocals. So several equations here that look very similar. These three are for the energy, and if you take the energy of a photon is equal to hf, and if you use speed of light is equal to lambda f, you use these two equations, then you can derive these two over here. And this Rydberg constant is what you get when you apply these two equations and you simplify the constant over here. You just take all those constants and name it something else. In this case, the Rydberg constant. So I'm going to show you these equations here, but I'm going to sweep through this chapter and see where that equation first appears. There's these things on emission lines, which is one of the reasons why that n over there that you see in the denominator is a integer. So over here they show you that equation, very similar, except they replace the n final over here with a 2. And then n is only allowed to be 3, 4, or 5, and all of the integers above 2. So you can read about this if you're interested. Here we have some other equations, and you can see these equations have a different name depending on what is the n final state. So here n final is n equals 1. Here n final is n equals 3. Here n final is n equals 4. They each have different names. And that is shown, where are those graphs that I'm looking for? Right here. You see how the energy over here, we have a 1, 2, 3, 4, 5. The separation between n equals 1 and n equals 2 is the biggest. Separation between n equals 2 and n equals 3 is smaller, and then it gets smaller and smaller until n equals infinity. And you can see those little lines that go from a n final all the way to the n initial, which could be n equals 1, n equals 2. They have those different names over here. So pictorially, I want you guys to visualize this over here, and mathematically visualize this equation here with the n squared differences. Same thing over here, this little n squared difference. Same thing as what you saw at the beginning, these little n squared equations, here, here, and here. So you can take a look at this. This is a kind of way of thinking about the electron and nucleus, right? They show you some pictures here. They show you some interesting equations here that are very helpful. Take a look at this. These equations are also very helpful. Read up on this stuff. Here's a energy conservation equation that is used to derive the final equation. Here's that alpha naught, which they actually call the Bohr radius, and all the equations that I showed you guys here today. So I'm not showing you this because this is all the equations that I put on the page. And just below this, Over here, we have a quick quiz and we have an example. So let's take a look at the quick quiz very quick. A hydrogen atom is in its ground state. Incident on the atom is a photon having an energy of 10.5 electron volts. What is the result? The atom is excited to a higher allowed state. The atom is ionized. The photon passes by the atom without interaction. So a hydrogen atom is in its ground state. Ground state means n equals 1. We hit it with a photon of 10.5 electron volts. What is the result? A, the atom is excited. B, the atom is ionized. The photon passes by without interacting with the atom. So what I will say is C, the photon passes by the atom without interaction. Why am I saying this? Because 10.5 electron volts is the number given to us. And if you look over here, take a look at this number here. This is 13.6 and the units are electron volts. So the ground state, which is defined by this n equals 1, is at energy negative 13.6 electron volts. Over here, we have 3.4 electron volts. So the difference between those, if I have negative, the difference between 13.606 and 3.404, forget about the minus signs. I'm just looking for the difference between those two energy states. We can see that it's 13.6 minus 3. Take away the 3, it's 10.6. Take away the 4, it's 10.2. Interesting. Okay, so I might be wrong here. So I'm basically just finding the energy difference between the n equals 1, which is the ground state, and the n equals 2, which is the first excited state. What I'm doing basically is applying this equation over here, right? This equation, the energy difference between those two. It comes in specific chunks. How big are those chunks? It is literally the difference between these two things here, which you can kind of derive from that equation, the difference between the energy levels. That is some of the equations over here, right? Not that one, actually. It will be exactly... it's not even that one either. Anyway, it's one of the equations that I showed you there, not with this n, but with the n squared minus n initial squared. So I found out that the difference between the n equals 1 and n equals 2 is 10.2 electron volts. And you need to have enough energy in this photon to actually push the electron to the next level. If you had just less than that, the photon will pass by without being hit. So the reason I said part C was because I thought that this 10.5 had to be exactly 13.6 or over. But because we took that energy difference, I think it looks like the atom is excited to a higher allowed state. And that higher allowed state is the n equals 2. There's not enough energy to push it to the n equals 3. There's not enough energy to ionize it. Ionize it means you send it to the n equals infinity. You literally rip it away from the nucleus. So that is my answer for quick quiz 42. I'm going to check the solutions a little bit later and see if it's right. But right now I'm going to do quick quiz 42.2 just to get my blood warm, get my brain working. A hydrogen atom makes a transition from the n equals 3 level to the n equals 2 level. It then makes a transition from the n equals 2 level to the n equals 1 level, which transition results in emission of a longer wavelength photon. So longer wavelength means shorter frequency. Is that true? Yes. Shorter frequency. Shorter frequency. If the frequency is lower, the energy is lower. So longer wavelength means low energy. So the lower energy is between n equals 2 and n equals 3. Because as you saw before, the jump between n equals 1 to n equals 2 is the biggest one. The jump from n equals 2 to n equals 3 is smaller, and then it gets smaller and smaller. So I'm going to say the first transition between n equals 3 to n equals 2 is the lower energy, therefore the lower frequency, therefore the higher or longer wavelength. I don't know if that made sense. We're going to check the quick quiz as well. But that is kind of just how I want to go through some of these problems. Ask myself a question, see if I can explain it with the theory. You guys should do the same thing. If you run out of these quick quizzes, just go to ChatGPT and say, hey, I'm doing an atomic physics. You can plug in, copy paste these 2 questions and say, these are some 2 questions that I tried. Give me something similar so I could practice. And also, if you don't understand, just copy paste these into ChatGPT, ask it like, hey, what is going on here? Please explain it to me. You're going to be rocking. Electronic transition in hydrogen. Let's just read this. I'm not going to solve it for you because the solution is right here. We're literally going to see it together. The electron in hydrogen atom makes a transition from the n equals 2 energy level to the ground level n equals 1. Find the wavelength. Literally, take one of these equations here. In this case, it could be this one here for the wavelength because they're asking you for the wavelength. But if you don't have that equation and you have this equation in the equation sheet, you could plug in the final, you could plug in the initial. All of these things are constants. You can spit out an energy. This energy, you could use this equation over here to find the frequency, and then you can use this equation over here to find the wavelength, right? H is a constant. E is obtained from this equation. Everything in this equation is known. It is given to you in the problem. Like I said, H is a constant, so you can determine F by isolation in some algebra. And then here you have speed of light, which is a constant, which is given to you. If you determine F from this equation, which you determine from this equation, you can now isolate for lambda. Or you could just use this equation here, but I don't think this equation is on the equation sheet. So that being said, let's take a look if that's what they do. They actually use that equation directly, and then they pull out the frequency, which is what was being asked. I think I was confused and I thought they were asking for the wavelength. No, it does say find the wavelength. Okay, find the wavelength and frequency of the emitted photon. So they find the wavelength here, right here, boom. And then they use C is equal to lambda F to find the frequency, boom. So try that out. That is the solution of the book. B, in interstellar space, highly excited hydrogen atoms called Rydberg atoms have been observed. Find the wavelength to which radio astronomers must tune to detect signals from electrons dropping from the n equals 273 level to the n equals 272 level. So you have two n's, the initial, the final. What are they asking you? Find right here, find the wavelength to which radio astronomers must tune to detect signals. Okay, you could literally just find the wavelength, plug in the numbers here into the equation over here, which is exactly what they do right here, and then boom, they find the wavelength in meters. Amazing. C, what is the radius of the electron in orbit for a Rydberg atom? Sorry, what is the radius of the electron orbit of a Rydberg atom for which n equals 273? And here you could see they use an interesting equation. They take 273, square it, multiply it by this 0.529 nanometers, which, as you may have seen before, or you may remember from sweeping through the book over here, here's actually the equation. They have an extra z over here. But this little a is this thing over here, the Bohr radius. So I think the Bohr radius is the closest an electron can get to the nucleus, for example, of the hydrogen atom. It turns out that radii of Bohr orbits in hydrogen, you can use this equation here to find the radius. How do you know that if the equation isn't on the equation sheet? Well, you don't, and if you don't remember this and you're asked a question about this, you are screwed. So you have to remember that equation, and that is what they use in part C. D, how fast is the electron moving? Again, we have another equation for velocity that they have introduced. If you don't know it and it's not on the equation sheet, you're screwed. But reading up about these equations here and the theory, this equation, the Rydberg equation with all of these n's, the theory uses all of these things, the radius right over here in part C, the velocity right over here in part D. And keep that in mind when you're kind of walking through problems and solving homework problems. What do these people use to solve the answer? And can you do the same thing if you're just in a room with a pencil and paper and no other support? So I just wanted to show you guys this. Now I'm going to zoom through because the rest of this chapter is about the quantum stuff. Like here's this equation that looks very similar to what I wrote in the beginning. It's actually identical. Actually, there's some minus signs here. The minus signs are kind of strange. Sometimes they appear, sometimes they don't, depending on how you kind of organize your system. But I'm just going to sweep through because this stuff is not important to the video today. I just want to go to the end of the book. I'm sweeping kind of slow in case there's anything important here. Look at this stuff. This is crazy, bro. This is the little angular momentum orbitals. Super interesting, but we're not going to look at that for today. What I do want to do is go to the end of the book. Sorry, the end of this chapter specifically. Let's zoom through. And I want to pick a problem. So here's the end of the book. This is the summary. You could also look at the summary. They summarize a lot of the equations that are interesting. You could literally just get a summary like this. Boom. Read it for 2 minutes and you should be pretty good prepared for the exam, but you have to do some practice as well. So those are some conceptual questions up there. You can look at those if you want, but what I'm interested in is the problems. And right here, atomic spectra of gases is actually where we used this question. So I'm going to pick a problem from this section. Early models of the atom, I think, moves beyond what we were looking at. So I'm just going to stick with these first 5 problems and pick one. Let's read number 1. The wavelengths of the Lyman series for hydrogen are given by blank, the equation that we saw. A, calculate the wavelengths for the first 3 lines in this series. I don't really want to do that. You just plug in n equals 2, 3, 4, and then you plug in, chug away, and get lambda. B, identify the region of electromagnetic spectrum in which these lines appear. Interesting question. So you Google search electromagnetic spectrum. What does it look like? Turns out that visible light is in a specific range. I remember this range by 400 nanometers to 700 nanometers. 400 is around blue light. If you go shorter than blue, you get to gamma rays and stuff that's invisible to the human eye. 700 is red light. If you go beyond 700, you get infrared and radio waves and all that. So all of that is invisible to the human eye. Turns out that these Lyman series, they will spit out some specific wavelength. You can see if that's in the visible range or not, and what kind of device you need to measure those. Interesting problem. Try it out if you are interested, but I kind of want to see something a bit more tricky for this video. The wavelengths of the Paschen series for hydrogen are given by, and they say pretty much do the same problem as number 2. Number 3 is in blue. I don't know what that means. Maybe it's more difficult. An isolated atom of a certain element emits light of wavelength 520 nanometers when the atom falls from its 5th excited state into its 2nd excited state. The atom emits a photon of wavelength 410 nanometers when it drops from its 6th excited state into its 2nd excited state. Find the wavelength of light radiated when the atom makes a transition from its 6th to its 5th excited state. You know what? I think this is a good problem. Because it's weird. It's like almost like a riddle. And it's going to make me kind of test my knowledge. I have no idea what the solutions. So we're going to do it here together. Let's set up the problem. Okay, let's circle what's important. An isolated, whoops. Okay, I can't circle on that, but I'm going to just write down what's important. Isolated atom of certain element emits light of wavelength 520 nanometers. This is wavelength 1, let's call it. When the atom falls from its 5th excited state to the 2nd excited state. So let's say here n equals 5. This is 4. This is 3. This is 2. Actually, they're bigger as they get closer down. So maybe this is a bad picture. Maybe we start with 1, 2, 3, 4, 5. So this is n equals 5. This is 4, 3, 2, 1. So when the thing goes from 5 to 2, it goes from over here. Let me actually pick a red. It goes from here all the way to here. So what we have is n initial is equal to 5, n final is equal to 2. Let's see if there's some more information here. The atom emits a photon of wavelength 410 nanometers when it drops from its 6th excited state to the 2nd excited state. Okay, so we have another one here. This is n equals 6. And this green one goes from the 6th to the 2nd. And here we can write it. N initial equals 6, and final equals 2. When the atom, when it drops from its 6th excited state to the 2nd excited, find the wavelength of light radiated when the atom makes a transition from its 6th to its 5th. So our question is, from the 6th to the 5th, what is the light emitted? So lambda 3 is equal to question mark, n final is equal to 5, n initial is equal to 6. So these are the questions. I don't know why they give us these things over here. Maybe they give us this so that we can plug it into the equation with those little n squared. We can plug it into this equation here, and maybe we can isolate for kind of an unknown value here, and then we can get the final form of this equation and then use this information here. But to me, We're looking for wavelength, right? So I remember this equation here, F is equal to KE, E squared. I have 2A subscript 0H, and then here I have N final squared minus N initial squared, reciprocals of these bad boys. So to me, I don't understand why this information is given to us, because everything inside this function is a constant. KE is a constant. It doesn't change depending on what the heck the system is. Always a constant. Electron charge is always a constant. A subscript 0 is also always a constant. I don't know if that changes with respect to the atom you're talking about. Maybe it does. You've seen some equations with this Z. Z equals 1 for hydrogen, if I'm not mistaken. And I've seen other problems, Z equals 74 for tungsten or some other material. So maybe this is included, but I can't see it in this equation. So I don't know why it would be included. And H over here, Planck constant, we also have it. So to me, it looks like we could just take these two numbers, N equals 5, N equals 6, plug them in here. Everything in this equation is known, and then we can isolate for F. Then when we have F, we can use C equals lambda F. We can isolate for lambda, which is equal to CF. After we get F from here, we could plug it in. C is a constant, and then we can isolate for lambda, which is what the question is asking us over here. So I'm going to do that, then I'm going to check the solution, see if it works. This is just my strategy. I'm using an equation from the equation sheet. No second guessing, no questions. No idea if something is wrong. So we're going to try it out. Let's try it out over here. Let me pull up my equation sheet so that I can see what constants I need to use here. Okay, we have KE 8.987 times 10 to the 9. We have Newton meters squared, Coulomb squared. Cool. Then electron charge is minus 1.6 times 10 to the negative 19 coulombs. Remember, this whole thing is squared. On the bottom, we have 2. This alpha, or sorry, A subscript 0 is 0.052 nanometers. And then here we have H, which is also given to me. It is 6.626 times 10 to the negative 34, and this is joules times seconds. Nice. So I ran out of a bit of room here, but I can just grab this guy. Move this here. Now I will put this here. So what did we say the N final was? We said that was 5. 5 times 5 is 25, minus 6 times 6 is 36. Is that true? So right now, instead of just plugging the numbers in, I'm just going to do a unit analysis to see if all the units check out and look good. So we have these units here. Then we have Coulomb squared, because that whole thing there is being squared. Here I have to convert this nanometers to times 10 to the negative 9, because then I have meters left over here. I want to have meters. Then we have joules, then we have seconds. Okay, it looks like coulombs and coulombs cancels over here. It looks like meters cancels with one of these meters here. And what we're left with does not look like a frequency to me. Remember, we're looking for frequency. We have Newton meters on the top, and then we have joule seconds on the bottom. So how I can expand this is, I remember an equation for newtons is Newton's second law, F equals ma. This is newtons, which is equal to mass, which is kilograms, and acceleration is meters per second squared. Then I remember another equation for joules, which is kinetic energy is 1/2 mv squared. And I remember kinetic energy has units of joules, 1/2 is unitless, mass is kilograms, and velocity is meters per second, and velocity is squared. So now I have these two things over here, these two equations, which I can see in my equation, in my unit analysis over here. So I'm going to just replace those. We have kilogram meters per second squared times meters, right? That is the meters left over here. On the bottom, we have kilogram meters squared seconds squared times seconds. Now we can see kilograms cancels with kilograms, meters and meters cancels with meters squared, second squared cancels with second squared, and we're left with just seconds on the bottom, which is 1/seconds, which is hertz, which is the correct unit that we're looking for. So I can tell that by this entire thing. By the way, notice that the thing inside the brackets over here is unitless. Just a number, no units. So all of the units that I checked over here, they cancel out and they give me the correct units for frequency. That is the case with all equations, but I'm just doing this unit analysis to make sure that my calculation is good. I'm not just wasting time doing some crazy stuff here. What I get at the end after plugging this into my calculator is 0.04 times 10 to the 13, and we just saw that the units were hertz or 1/seconds. So this was a problem in the book. I did it kind of blindly to see how I can manage with the equations. Now I'm just going to check very quickly the solution. My bad, I completely forgot that they were asking us for the wavelength. So the wavelength was c over f. So we have 3 times 10 to the 8 meters per second divided by 4.04 times 10 to the 13 seconds to the minus 1. Seconds to the minus 1, all the units cancel. Here we get meters. And what is this? Let me plug this into my calculator. This is 7.43 micrometers. And the book answer is 1.94 micrometers. So what did we do wrong? Well, we solved the problem and we saw that the answer that we got was not the same as the answer in the book. They're close, right? In the same micrometer range, but the book got 1.9, I got 7.4. So what is the problem? Well, remember all of the things that we got over here at the beginning? We got these transitions. So they gave us this transition here in red, this one in green. Here I wrote it in red, here I wrote it in green, and they told us the wavelength that it was emitted. And then I said, okay, why do we need this? We could just use this equation here, plug this stuff in, and spit it out. Let's read the problem again. It says an isolated atom of a certain element emits light. Okay, so I think the problem was that the equation that is used here works only for hydrogen. And there has to be some kind of Z value over here. This was my suspicion in the beginning. And it turns out this is the common mistake that you can run into. So what the book actually does is it uses these values. Let me actually show you the solution of the book. So it says the fifth excited state must lie above the second excited state by the photon energy. So what it does is it calculates the energy between this transition from 5 to 2. How does it calculate this? It literally does HF is equal to HC over lambda, the equations that I showed you, and then they plug this stuff in. This is a constant, this is a constant, and this lambda is actually given to us. This lambda is this first one, 520 nanometers. So in here, they plug in 520 times 10 to the negative 9 meters. And then since they have H, they have C, they can calculate the energy transitioning from 5 to 2. Then what they do is they find the energy transitioning from 6 to 2. Right, which is what was given to us as well over here. Energy transitioning from 6 to 2, and they tell us this is 410 nanometers. So we have energy from 6 to 2 is equal to HF. We have HC over lambda because we use this equation over here. And then they plug in over here 410 times 10 to the negative 9 meters for the wavelength. Then they can get this energy over here. And then what they say is the sixth excited state is above the fifth by, and they take this difference over here. So the energy that they calculate for this after plugging all the numbers is 3.82 times 10 to the negative 19 joules. And the energy they get for this transition is 4.85 times 10 to the negative 19 joules. Okay? These two energies are calculated. Different path of solving the problem that I chose, which is actually why I chose a problem at random and tried to do this with no cuts to show you that you picking a problem and doing this are most likely going to end up in a interesting kerfluffle. That's the point of all these problems at the book. They're supposed to test your understanding. They tested my understanding. Even though I'm your TA, I've looked at this shit for years, I am still getting this wrong. So, I don't know if that makes you feel better or feel worse, but the whole point of this video is to show you that you can do this without too much energy. You could try it out on your own. I mean, maybe it does take a lot of energy. I'm trying to give you the motivation here to do it. And then check the book problem and see where the kerfluffle happened. Once you've actually outlined what the problem is, I know you might be angry and be like, bro, how am I expected to do this when very easily I could just choose this equation over here and proceed forward just like how you did? Well, that's the whole point of this video. I'm trying to show you that you can make a mistake at any point. Even if you study this content for years, you can make a mistake. But there's no point in getting angry. The point is to just look at what you missed, try to understand that this energy kind of solution is better, and why is it better? Why did our method not work, and why is this the method that's chosen? And also, if both methods work well, then why is it that we got, where's my solution? Why is it that we got two different answers when we did it our way and we did it the book way? So anyway, what's happening here is that they're taking 4.85 times 10 to the negative 19 joules. They're subtracting this from 3.82 times 10 to the negative 19 joules. The answer they get is 1.03 times 10 to the negative 19 joules, right? Why are they taking this energy difference? Well, remember, this energy difference was from 6 to 2. This one was from 5 to 2. So, when you take the difference here, it's almost like you're asking, what is the energy of going from 6 to 5? You see what I'm saying? Because both of these transitions, let's say this is 6, 5, then we have 4, then we have 3, then we have 2 over here, then we have 1. This is 1, 2, 3, 4. We are given the energy of this thing going down to here, and then we are given the energy of this thing going down to here. If I take the difference of these two, right, basically I'm taking the length of this, subtracting the length of this, what do I get? Well, I get just the length of this over here, which is exactly the transition they are asking for from here to here. So once you have this energy, the energy from 6 to 5, you see how this is kind of something that I overlooked. You may have overlooked as well, this kind of energy thing, but it teaches you something new about how the mechanics of all of this atomic physics stuff works under the hood. So now that we have this energy here, we found it in an interesting way. We saw that the way we used in the beginning, the original suggested way, which is just use the equation from the equation sheet, was incorrect. Now we have this, and what we could do here, and what the book does, is it literally uses this E is equal to HF. You have E, you have H. Now you can find F is equal to E over H. But you're not looking for F. Remember, you're looking for lambda. So we can also use C is equal to lambda F. We can isolate for F and see that, isolate for lambda, or you know what, let's isolate for F. F is equal to C over lambda. And we can replace this F over here with C over lambda. Now we can just flip some stuff and we get an equation for lambda, which is HC over E. Now you have E. What is the E? It is this E that we found in an interesting way of subtracting stuff. And then we have H and we have C. So let's actually do this. We have 6.626 times 10 to the negative 34 joule times seconds, right? We have 3 times 10 to the 8 meters per second. These things are being multiplied in the numerator. Here on the bottom, we have our newly calculated energy, 1.03 times 10 to the, what was the units? Negative 19 joules. And I think that's pretty much it, right? So let's do some unit calculation, unit analysis here. Cancellation of units. We have joules here, cancels with these joules. These units cancel with these. And then we have meters left. So the whole final answer is in meters, which is exactly what we're looking for. And we see that the answer is 1.94 times 10 to the negative 6 meters, or 1.94 micrometers, which is the answer in the book, which is just me looking at the solution of the book. So okay, let's look at a big overview. We have a question. I outlined some important information. Then I instantly noticed something familiar to me, and I was like, okay, let me just pick a pathway. I picked this equation and I bulldozed forward. Plug in some numbers. Unit calculation gave us the right answer. And then at the end, well, we found a frequency, but the question was actually asking us for wavelength. So I pulled this out and I got this wavelength over here. Then I checked the answer in the book, right? Because I just tried this on my own terms. I didn't know what was going to happen. My answer does not match the book answer. At this point, I check in the book, what are they doing? They're doing this interesting thing here. The question is, and this is the homework for you guys, why are they doing this? My suspicion is, in the question, they say an isolated atom of a certain element. So then I was saying over here, the equation over here could just be for the hydrogen atom. Is this true? I'm not sure. You guys have to read a little bit in the book, try to figure out if that's actually the case. But you have to ask yourself now, why is it my strategy over here did not work and the book strategy did work? And the book strategy was using this difference between energy levels, information that was given to us in the problem. So I hope this was helpful. I hope you guys don't feel a little disheartened that an equation in the equation sheet that you instantly think of using, it will lead you down the wrong path. As you saw in this video, this is authentic. I just picked a random problem. I didn't check the solution. I just kind of proceeded with kind of my experience and what I thought I should do. And I was wrong. But that's not a problem. Don't stress about being wrong. This taught me something new. And now that it taught me something new, although it's something new I have to learn, which might be annoying, you might feel like your brain is full of energy right now, full of information. You don't have any more room to fit any new information. This should at least kind of help you guide you into different areas of research and asking yourself, like, what's wrong here? Where did I go wrong, and why is my method not working? Why is the book method working? So do this with every single problem, every single homework problem, every single problem you see in the book. And yeah, I hope you guys enjoyed. Leave a comment down below if you are interested in any other problems. Good luck studying. Peace out.